Let's talk about data representation. How data is represented inside the computer. So let me set the table for you first. So in our daily life, we use a number system that's based on 10 and is also called decimal system. And why we use a 10-based system, right? And in the ancient days, when you look at ancient Greece or Egypt, China, they all came up with the decimal number system independently. And back in thousands of years ago, they don't really travel and talk to each other, right? So the explanation for that is that we all have 10 fingers, right? So if, like, in the cartoons, the cartoon characters generally have 8 fingers. So if we have 8 fingers, we probably would have a 8-base number system. Okay. Now, computer, as we all know, is zeros and ones, and so it's a base 2 system. And why just zeros and ones? Well, because semiconductor, the logic gate can have either on or off. And if you use on to represent 1, off to represent 0, that's kind of you only have 2 states, right? So for computer, it only understands zeros and ones. Okay, now let's look at a decimal number, right? Let's say how many days in a year, like 365. So it's base 10. So the way that let's say we try to convert 365 from a decimal system to a decimal system, right? The way to look at it is that on the right-hand side, this digit, okay, is called the least significant digit. On the left-hand side, the 3 is the most significant digit because, one number change is bigger than any of these other 2 position change. So in the first position here, it actually represents the base to the power of 0. And the second position is the 10 base power to 1. And then on the third position is 10 to the power of 2. Now the way to do the conversion is this. You use 3 multiplied by 10 to the power of 2 plus 6 multiply by 10 to the power of 1 plus 5 multiply 10 to the power of 0. Now this would be 300, right? Plus 60 plus 5, right? Because 10 to the power of 0 is 1. So now is 365. And the same method applied to any base number, any number system that's based on anything that's greater than or equal to 2. Okay. So what we're going to learn in this video, we're going to learn binary numbers, how to translate between binary and decimal. You just saw one example to translate between decimal to decimal. We're going to use the similar method to translate between binary and decimal. How to do binary addition, how to add two binary numbers. Integer storage sizes. And then we are going to discuss a 16-based number system called hexadecimal. How to represent integers using hexadecimal numbers. And we learn how to translate between decimal and hexadecimal, and hexadecimal subtraction. Okay. And how do you represent, in terms of integers, right? There are signed and unsigned integers. How do you do binary subtraction, right? So if it's you subtract like A minus B, if B is actually a bigger number than A, you get a negative number, right? And how do you represent a negative number with binary representation? And lastly, we talk about character, how to store characters in binary form. Okay. Binary numbers, there are only two digits, 1 and 0, right? And they represent the circuitries on or off. And if you look at a number like this, right, 1 0 1 1 0 0 blah blah blah. So this is a 16-digit binary number. Okay, all the way to the left. In the place 15, because it starts from the right, from 0, right, to the 15. That bit is the most significant bit. And then on the other end, at the place 0, it is called the least significant bit. So with binary number, each digit or bit, it's either 1 or 0, as you know. And each bit represents a power of 2. So just recall what we did earlier with the decimal number, which is base 10, right? In here, it's based on 2. So the least significant bit represent a base value of 2 to the power of 0. And then the bit to its left is 2 to the power of 1, and all the way to the 2 to the power of 7. Okay. So if you try to convert this number, this binary number, okay, and you use 1 multiplied by, let's see, power of 0, 1, 2, 3, 4, 5. 1 multiplied by the 2 to the 5th, right? Which is 32. And then you plus 2 to the power of 0, 1, 2. That's 2. Okay? And then you add the last one. 1 multiplied by 2 to the power of 0. And 32 plus 4 plus 1, that would be 37. So the bit position value starting from right to left is 1. So if this bit is 0, 0 multiplied by 1 is still 0. If it's 1 multiplied by 1, then it's 1. And then the place value of the second bit to the right is 2. Third bit is 4, 8, 16, 32, so on and so forth. And the place value in a 16-bit binary number, the most significant bit represent a value of 32,768. Okay. Now, how to translate, like I showed you earlier, how to translate binary to decimal, right? So you basically take the digit, multiply by that particular digit's place value. And if it's in the nth place from the right, it would be 2 to the power of n minus 1. And you add them all up. Okay? Now let's use one example, right? 00001, 001, which is an 8-bit binary number. So if you go from the right to the left, right, you can ignore the leading zeros. And then you start with the first one, okay? The first one, what's the place value of this bit here? It's 2 to the 0, power of 0, power of 1, power of 2, power of 3. So it would be 1 multiplied by 2 to the power of 3 plus 1 multiplied by 2 to the power of 0, which is this number. And you can also ignore zeros in the middle, right? And you add these two numbers up. This is 8, this is 1. Then this binary number represents number 9 in decimal. Okay. So, and we can do a practice of what does this 0010, 1101 represent? And you use the same method. And the first one is in the position 5 from 0, right? From the right hand side. 0, 1, 2, 3, 4, 5. So it's 1 multiplied by 2 to the power of 5, followed by, this is number 3 place value. It's number 3 bit from the right hand side, starting from 0. And you add 1 to the 2 to the power of 3. And then you add this one. 1 multiplied by 2 to the power of 2. And then you ignore this one because it's 0. And the last one is 1 multiplied by the 2 to the power of 0. And you get number 45. By the way, this is called peer talk, is that for a in-person class, and you guys will talk to each other and figure this out yourself. Okay. How do you translate unsigned decimal to binary, meaning positive numbers, positive integer decimal numbers to binary? So the way it works is that you take a number, let's say 37, okay? You repeatedly divide it by, or you look at the, you divide the number by 2. And then the division will come up 2 parts. One is quotient, the other is remainder. 37 divided by 2 would have a quotient of 18, right? Because 2 times 18 is 36. 36 plus the remainder 1, that would be 37. So, so you divide it by 2, right? And then you get the quotient, and you get the remainder. And then you take the quotient and divide it again. This time, 18 divided by 2, 18 is actually an even number. Divided by 2, you get 9. The quotient is 9, and the remainder is 0. And then you take 9, divide that by 2, you get a quotient of 4 and 1. Okay. So the lastly, and you have a quotient of 1. 1 divided by 2, you get a quotient of 0, and you get a remainder of 1. Once the quotient reaches 0, you are done. Now the binary number would be, you are going to look at the remainder from bottom up. Okay, it would be 1, 0, 0, 1, 0, 1. And that would be the binary number. Now you can verify that by doing the conversion we did earlier. So that's the method to translate unsigned decimal to binary. Now, how to add two binary numbers? And just like what you learned in elementary school, how to add two decimal numbers together, the technique is exactly the same. So here we are going to add two binary numbers, and 000000100. That in decimal form is 4. And you add that to 000000111. That's in decimal form, it would be 7. Okay? The way you do it is that you start from the least significant bit. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is what? There's no 2. Right? Just like in the decimal, when you add 5 and 5, you get 10, right? So 1 plus 1, it's actually 10. Now you carry the 1 to the next bit to the left, which now is 1. And then the remainder is 0. And then you're done. And then you can calculate to verify whether this is indeed number 11. Okay? So this is 1, represent what? 2 to the power of 3, which is 8. 8 plus, this is 2 to the power of 1. So 8 plus 2 is 10, right? 10 plus 1 is 11. So that concludes our video on decimal representation and conversion between decimal numbers and binary numbers. In the next video, we'll talk about hexadecimal integers, which is based on number 16.